You ready?
Mhm.
All right. Hello, everyone. Thank you so much for coming to Junwon's master's thesis talk and also his speaking qualifier. We have both of his committee members here, Max and Jeff, as well as Michelle now, who's going to be on Zoom. And we're going to follow standard protocol, which is Junwon's going to give his talk. If you have any immediate questions, they're burning, they're pressing, you have to get them out specifically about details about the work that you're seeing. Feel free to interrupt, but we're going to hold questions until the detailed questions and discussion until the end. What we'll do is we'll go with kind of most OOD to keep it on theme first with questioning. So maybe we'll start with like Max, and we'll do Jeff, and we'll do me, and then we'll do Michelle, and then we'll open it up for audience questions. Junwon will speak for about like 45 minutes or so, and then we'll do that. All right, Junwon, take it away.
Great. Thanks for a great intro. And it's really my big pleasure to have the opportunity to talk about my research exclusive for an hour on a good day, which happened to be my birthday, in front of my committee of actually 4 professors. So anyway, robotics is advancing rapidly, enabling robots to perform complex tasks that could only be performed using raw observations such as camera images. And worry models are one of the core techniques for learning such visuomotor policies. But are these policies actually robust? And what does even robustness mean for this visuomotor policy learning? So today, I will talk about how to make robots that use worry models robust to uncertainties in those models. So worry models have recently attracted significant interest in robotics, and their powers lie on the ability to predict the future outcomes of robot actions without analytic understanding of the underlying systems. For examples, the videos shown here are not real. They are all generated by worry models conditions on the robot actions for tasks such as humanoid manipulations and autonomous driving. A worry model is basically a learned model, conditions on past observation and robot action, generating future outcomes of directly in high-dimensional observation spaces. And this allows us to predict different future outcomes and for different candidate actions without physically executing them in the real world, which makes it possible to learn or evaluate robotic policies that are difficult to model analytically by all simulating the consequences of robot actions without physically executing them that may be unsafe in the real world. At their core, worry models are generative models that learn how the real world evolves. So given a fixed data set of robot interaction data with environment from our, for example, real planet Earth, consisting of observation, robot action, and the next observation sequences. And the worry model then learns to predict the future outcomes or future videos by minimizing its prediction loss, which is supervised learning on this fixed data set. And to just briefly introduce, there are 2 dominant paradigms for worry models, both of which have shown promising results in predicting the future outcomes of robot actions, thus for robotic control. The first is the latent worry model, which jointly learns an encoder that compresses high-dimensional observations into a compact latent space, and the dynamics model simultaneously that predicts the next latent condition on the previous state and the robot action, where the predicted latent state can be decoded back into the observation. The second is the video worry model, more recently introduced, which directly generates the future observations as videos using more powerful generative models, such as diffusion models recently. So both paradigms have shown promises in robotics from vision-based planning for like finding a diamond in this Minecraft environment, which is a tall example, and to evaluating and improving control policies, such as robotic manipulation, and even ensuring like hard to specify safety constraints, such as preventing Skittles from spilling. And they are all learned through world mode imaginations, only using camera observations without like privileged state information or analytic understanding of the world. So world models are good, and like robotics are improving. So because world models give robot imaginations, and we can use them to scale robotics to real world or vision-based tests. However, I want to say, but things are not that easy in real world. It's not always easy. So maybe someone very rigorous about robotics might ask, is a policy learned through all the world model imaginations actually reliable in the real world? And someone who is always a bit pessimistic might say, not necessarily. It's almost surely not reliable. And we should ask, why is it? So being a little sad, we should ask why. And I would say this is because world model imaginations are uncertain, which means the future imagined by a world model can significantly differ from what actually happens when the robot executed that action in the real world. So to understand this, let's take a look at what state-of-the-art world model imaginations actually look like. So here we again imagine what happens when the robot drops a coffee bag. And in the real world, dropping the bag from a high position causes the coffee beans to spill, as shown in the top, which is clearly a failure. However, the world model sometimes imagines that nothing spills inside the bin, possibly because it imagines there are no coffee bins inside the bag. Or consider this driving scenario, I want you to pay attention to the cyclist right next to the ego vehicle. So when we imagine how the cyclist will move in the future, the cyclist here suddenly evaporates or disappearing in the imagination. And turning what should be a dangerous situation because it risks a collision with the ego vehicle into a safe scenario. So even with all the recent progress and many smart researchers working on making a better world model, their imaginations or their predictions are still very uncertain, which means the imagined future from the world model can be different from what actually happens in reality. So this naturally leads to my central question of research, which is when learning a policy using this uncertain world model, how can you do so robustly? And I believe the best answer to this question is to explicitly mitigate the uncertainties of the world model whenever we are using it for robotics. So it sounds simple, but we first need to understand where these uncertainties are coming from and what are the sources of these uncertainties. So suppose for illustration that the world model operates in one-dimensional space, very simple space, where the x-axis represent the modal input consisting of past observation and robot action, while the y-axis represent the prediction target, namely the future observation. We then collect training data from interaction with our planet Earth, shown here as gray dots, and we train the model with supervised learning on this fixed data set. So this blue line represents the learned model's prediction, while this blue shaded region represents the uncertainty of that prediction. So we can broadly divide the sources of this uncertainty into two categories. The first is epistemic uncertainty, which arises from limited knowledge of the system. So for the inputs never seen during training, as shown in this purple region, world model predictions can become very unreliable or out of distribution situations. So that are not because they're not represented in the training data set. So as they're lacking the knowledge, the world model imagination cannot accurately predict the futures. So suppose I want to imagine a radical scenario, which is throwing the coffee bag off the table like this. And I can tell I have never collected such a trajectory during my world model training data collection because it's really hard to clean it up. So lacking in real knowledge of what happens in this situation, the world model may hallucinate or generate just implausible or completely inaccurate imaginations that is actually different from the reality. Another source of the uncertainty is aleatoric uncertainty, which is inherent randomness due to some unobservable physical conditions or the behavior of other agents that the ego agent's action doesn't have any control over. This uncertainty even persists when the training dataset has sufficient coverages as shown in the red regions here. For example, suppose the robot drops a coffee bag again, and in the training data, depending on hidden factors such as how many coffee beans are inside the bag, we have observed both spilling events and non-spilling outcomes. So if the bag was nearly empty, it may not spill, but if the bag happened to be very full, the beans may spill. However, because the amount of coffee beans inside the bag is not observable to robots, because it is not observable from the camera images, the imaginations from that input of the world model still remains uncertain. So given these uncertainties of world model imaginations, the goal of my work is to make robotic policies using these world model imaginations robust to these uncertainties. And I think I can do it by explicitly reasoning about and thus mitigating both epistemic and aleatoric uncertainties in world models. So in this talk, I will first introduce a method for mitigating epistemic uncertainty in world models for learning a visuomotor policies. Specifically, I will discuss how to learn a safety filter that prevents robot from entering high uncertainty or out of distribution states, thereby keeping the system robust to epistemic uncertainties. I will then present a method for mitigating aleatoric uncertainty by steering world model imaginations toward plausible but high impact outcomes when imaginations have high aleatoric uncertainty. Before we dive in, the overarching thesis statement is visuomotor policy learning in world models can be made robust by mitigating both epistemic and aleatoric uncertainties, avoiding out-of-distribution regions where model predictions are unreliable, and reasoning over plausible outcomes of robot actions. So let's dive in. I'll begin with epistemic uncertainty, how to keep the robots within regions where the world model is reliable. So actually, there are many existing works in machine learning literatures for detecting out of distributions. But I think they are a bit irresponsible because they tell us we're doomed, we are out of distribution, but they don't inform us how to avoid that situation. So in this work, I will discuss not only how to detect out of distribution situations or out of distribution world model imaginations where world model predictions loses its reliability, but also how to proactively avoid entering such regions, achieving robustness. To study this problem, let's consider a task of learning a policy that prevents the Jenga tower from toppling using only camera observations. And I believe all of you have played the game of Jenga before, and a Jenga tower can actually topple in countless different ways. And suppose we want to learn a world model from a fixed data set of robot playing Jenga, and then use it to learn a policy that prevents the tower from toppling. And however, without spending my entire PhD life teleoperating this Jenga, it might be maybe nearly impossible to cover every possible scenarios that robot can interact with this Jenga tower. So even with my best effort to teleoperate the robot and collect training data for training the world model, the dataset still has some insufficient coverages or missing dataset. So as a result, the world model is expected to exhibit high epistemic uncertainty coming from limited knowledge in scenarios where my interaction was limited. So we study how to mitigate epistemic uncertainty in the context of learning a latent safety filter. Specifically in this work, I will focus on using a latent world model that operates in a compact latent space to prevent failures. So intuitively, the goal of the latent safety filter is use world model imaginations to learn a visuomotor policy that prevents failure, in this case, the Jenga tower from toppling. So we first train a latent world model on a fixed data set I collected so that it can predict the future latent states conditioned on the robot's action and previous states. And on top of the learned latent representation of the world model, we train a binary failure classifier. The failure classifier here, or just a cost function to be simple, measures whether a given state is failure or not, which means is it toppled or not. So it's kind of a just classifier. And using a contour theoretic framework called Hamilton-Jacob reachability analysis, we can learn a policy that minimizes the failure cost or prevents the system from entering the failure set. I will skip like deeper details on it, but intuitively, this latent safety filter is just a visuomotor policy that prevents the robot from entering the failure set. So it imagines the future outcomes of an action proposed by a base policy. And based on the imagination, if the action is predicted to enter the failure set, the safety policy proactively steers the system toward a safer state before it actually enters the failure set. So this is the basic setting of the latent safety filter. But as I mentioned, like the naively learned policy can still be very unreliable because of uncertainties of a world model, especially the epistemic uncertainty here. So to illustrate this, here is an illustrative example where we train a latent world model for image-based Dubin's car. So where the small black robot here navigates this scared regions. And the purple region on top here is a failure set. However, the training data set never includes trajectories entering the purple region. So for example, it's a cliff. That is a failure set is dangerous, but we have no experiences entering that cliff. So that region is out of distribution for the world model because the data coverage here was intentionally excluding entering such failure region. And we train a world model with this limited coverages of the data set. And we ask the trained world model to imagine what actually happens when the robot enters this region. And the trained world model, lacking knowledge, hallucinate a safe outcome when it was asked to enter this failure region. So we refer to the resulting failure, where world model hallucinate a safer outcome when it is actually an unsafe outcome, as an out-of-distribution failure. So applying this intuition to Jenga again, the world model has limited knowledge of some failure modes and exhibit high epistemic uncertainty when imagining entering those regions. So not all failures are covered in our training data set. So there are some unknown failure regions like this. So therefore, in such out-of-distribution scenarios, the worry model may hallucinate and fail to prevent these unseen failures. Here, as you can see in the video, the robot moves the Jenga block in an unfamiliar direction, which is unsafe. And the tower topples in the real world, while the model imagination, as shown here, remains safe. So the key question here is, how can robots avoid both known and unseen failures, achieving robustness to epistemic uncertainties? So the key insight here is that we can quantify the epistemic uncertainty in the worry model's imagination and use it as a proxy for identifying unseen failure modes, achieving robustness to epistemic uncertainty of the worry model. So there are known failures, which are represented in the training data. And therefore, worry model predictions are very reliable like this. And also unseen failures where the worry model lacks knowledge and its imaginations become highly uncertain. So to prevent both types of failure and thereby achieve robustness to epistemic uncertainty, we detect out-of-distribution worry model imaginations by combining epistemic uncertainty quantification and conformal calibration, and treat this out-of-distribution set as a part of the failure set. And this allows us to synthesize an uncertainty-aware safety filter that prevents both from the known failure set and also unseen failures, and we call it Unisafe. The learning policy then can proactively avoid known failure states as well as regions of high epistemic uncertainty, thereby keeping the system safe as well as in distribution, achieving robustness to the epistemic uncertainty. So here are more details on how we actually detect out of distribution. First, to quantify epistemic uncertainty in worry model predictions, we train an ensemble of latent dynamics model with each member initialized differently, but using the same training data set. And when the input to this worry model is out of distribution, the predictions for ensemble members will diverge. So we can use their disagreement score as a proxy for measuring quantifying uncertainties. However, we specifically want to capture epistemic uncertainty, which are coming from a lack of knowledge of the worry model, rather than aleatoric uncertainty, which reflects inherent stochasticity in the world. So worry model predictions can still contain aleatoric uncertainty in this case, especially if they are operating on the image space and they have complicated contact dynamics. For example, consider these two scenarios in which the robot removes the orange block in the tower in the same direction. So the resulting features are slightly different, which means they are uncertain, but likely because of inherent randomness in the block dynamics, not about epistemic uncertainty, which is coming from limited knowledge. So if our uncertainty quantification conflates these two sources of uncertainties, the resulting safety filter may become overly conservative, simply rejecting any uncertain scenario even when it is still in distribution. So therefore, our goal is to disentangle epistemic uncertainty from aleatoric uncertainty. And to achieve this, we adopt the Jensen-Renyi divergence, which first quantifies the total predictive uncertainty of the worry model and subtracts the aleatory component, leaving only the epistemic uncertainty part. So in general, this computation is intractable and requires Monte Carlo sampling. But when alpha equals 2, there exists a closed form solution, making the computation efficient. So once we quantify the epistemic uncertainty, we need to define the out-of-distribution failure set from this continuous scalar value. So this requires a threshold so that a prediction is considered out of distribution when its uncertainty exceeds the threshold and vice versa. However, choosing a meaningful threshold for detecting out of distribution, especially for this safety case, is not trivial. And to obtain a probabilistic guarantee, we use conformal prediction, a distributional-free calibration framework. I'm not gonna get deeper into this, but basically using a held-out calibration dataset, we calibrate the uncertainty threshold so that out-of-distribution predictions are detected with a specified probabilistic guarantees. So using the epistemic uncertainty quantification and conformal calibration to set a threshold, we define the out-of-distribution failure set and also include them to learn a policy that prevents entering the out-of-distribution. And here are the results of learned safety filter. In this experiment, a human teleoperator, probably me, is like teleoperating the robot to remove Jenga blocks, while the learned safety filter can override unsafe action to prevent failures. So as you can see in this video, Unisafe correctly prevents both seen and unseen failures by proposing safe and in-distribution actions, which are reliable, while keeping the uncertainty values below the calibrate threshold as shown in this orange dotted line. And another good thing of this one is when the base policy proposes us just safe in distribution action, the safety filter is not being overly conservative because they're only focusing on epistemic uncertainty, which freely allows the safe action without any interventions. However, this is the safety filter trained without including out of distribution predictions in the failure set. So when this uncertainty unaware safety filter encounters an unseen and unsafe action, it actually relies on overly optimistic or hallucinated imaginations where it imagines known failure when it actually failed in reality. So as a result, it fails to prevent the system from failure robustly, and the prediction exhibits high epistemic uncertainty, which was not used for the safety filter in this case. So the main takeaway from this work is that we can learn a policy that is robust to epistemic uncertainty in the worry model imaginations by detecting and also systematically avoiding out-of-distribution regions. And we achieve this by epistemic uncertainty quantification and conformal prediction. And we then incorporate this resulting out-of-distribution regions into the safety specification, allowing the safety filter not only detect them, but also to proactively prevent the robot from entering them. And a key algorithmic takeaway is that isolating epistemic uncertainty from aleatoric uncertainty is very critical so that it explicitly targets epistemic uncertainty so that it can robustly prevent failure while being non-conservative. So while we can achieve robustness to epistemic uncertainty, aleatoric uncertainty in wormhole imagination still persists. And I think addressing this aleatoric uncertainty is very essential for robust visuomotor policies and reliable robot operations in the world. Because as mentioned earlier, it cannot be eliminated even with intern-scale data collection. So data is not the problem. And we now tackle this second challenge, achieving robustness to aleatoric uncertainty in wormhole imaginations. So to study this problem, let's consider the task of robot pouring coffee beans into a bowl. And we don't want the robot to spill coffee beans all over the table because it's hard to clean it up. But even when the robot executes exactly the same motion or expert demonstration, the outcome can still vary depending on some hidden factors such as how many beans are inside the opaque bag or some random physics parameters like frictions that the robot cannot observe from camera observations. So if the bag contains only a few beans inside the bag, life is good. We can have a good coffee. But if the bag is full, the exact same motion can actually lead to a disaster. We need to clean it up first, so we don't need a robot. So we study how to mitigate this aleatoric uncertainty in the setting of policy evaluation and improvement using video worry models here. So I'm gonna use the video worry models in this case and study how to mitigate the aleatoric uncertainty of the video worry model imaginations. So in this setup, given an observation, the Visuomotor policy proposes a robot action. And rather than evaluating the proposed action directly in the real world, which could be costly and risky, we use the video worry model to imagine future observations of the observation sequences given a robot action. And if the imagined outcome is successful, the policy is good. And if not, we can search for better alternatives and use that signals to improve the policy. So this is the basic setup of policy evaluation improvement with video worry models. However, the challenge here is, as I mentioned earlier, that the same robot action can actually lead to different outcomes. For example, the same lifting action here may cause the beans to spill in one case, but not in the other. So in other words, the ground truth future outcomes in this work is inherently uncertain, especially we only relies on this partially observed system, which means we are only operating on this image observations where the full states are not fully observable. However, one good news is that recent video worry models, particularly those based on diffusion models, can at least represent these uncertainties. So rather than just learning a single deterministic future given a robot action, our diffusion-based video worry models learn a distribution of possible futures. So therefore, even with the same input, different imaginations can be produced, provided that the training data captures this variability well. So in this setup, let's assume that both the observations and actions, which are input to the worry model, are in distribution so that we can focus specifically on this aleatoric uncertainties that still remains with sufficient data coverages. And the core challenge for policy evaluation improvement with this video world model is that we lack a method to sample the critical outcomes that matter most to the policy, such as failures, from the distribution of the future we learned by the diffusion-based world models. Instead, we typically rely on repeated random sampling, or I will call nominal sampling, and we hope that that critical outcome we care about eventually appears within the fixed sampling budget. But if a failure is plausible, but extremely rare, we may need to generate like thousands of samples before actually observing it. And this makes nominal sampling inefficient and can lead us to incorrectly conclude that a non-robust, unsafe action is actually good within a limited sampling budget. So more formally, our goal is to make the policy robust to aleatoric uncertainty in the world models, following the robust control literature. So we assume we have a cost function that evaluates the generated video, such as test failure. So it evaluates if the video is showing a failure outcome or not. And we then seek an action that is minimizing this cost under its worst case plausible outcome, which could be solved in numerous ways for policy optimization, like reinforcement learning or just like model predictive control. But the key challenge here is lies in this inner optimization shown in this orange, which is imagining the worst case plausible future outcomes of a given robot action that maximizes cost. So we can view this inner optimization as steering the world model's imagination toward outcomes that maximize this cost of the futures while preserving plausibility of the imagination. For example, a nominal sample may have imagined that no beans are spilled at first with the same action. And given the distribution of the outcome after steering, however, the world model may reveal a failure outcome with the same action that is still plausible under the given robot action. And this allows to evaluate the robot action more robustly within our world model, whose prediction contain aleatoric uncertainties. Therefore, to achieve robustness to aleatoric uncertainty, the main problem we aim to solve here is to efficiently and effectively steer video world model imaginations toward high impact outcomes that still remains plausible given the action. So before we dive into our solution, let's briefly review how actually diffusion-based video world models work. So it is conditioned on the robot observation history and future action sequences. And the diffusion-based video world model transforms a Gaussian noise sample into a future video sample. So each initial noise sample, therefore, produces one possible future imaginations drawn from the model's learned distribution. So in a specific formulation, this generation of diffusion models can be viewed as a deterministic function of the initial noise sample, which means different noise lead to a different imagined future, and the same initial noise always lead to the same imagination. And this means to steer the video world model imaginations, we can rather optimize this initial noise itself rather than just repeatedly sampling different outcomes from these diffusion models, which is searching for a noise sample that generates a critical outcome we are searching for a robust policy evaluation and improvement. So the next question for this optimizing initial noise is, how can we actually guide this optimization so that it generates high impact yet plausible outcomes of the robot action and efficiently? And one major challenge here is that the Gaussian noise we want to optimize, typically used by video world models, is extremely high dimensional. For example, it's 1 million dimension for some state-of-the-art world models, which is really tricky and hard to optimize. So as a result, just random sampling or zeroth order optimization suffers severely from the curse of dimensionality, where generating even a single sample takes about a minute. So to solve these challenges, the key idea is to combine two different objectives for optimizing the initial noise. First, we use the semantic objectives that leverages gradient signals from vision language model, which reasons about what is happening in the generated videos. And the dense gradients from this vision language model can efficiently guide the optimization of the high dimensional initial noise that generates scene-specific target critical outcomes of robot actions that matters for the policy. And we also ensure the steered imaginations are still plausible under the learned world model so that we can use the world model more reliably and meaningfully. And we call this method StressDream. So it basically has an inference time prompt asking whether a target event is occurring in the generated video or not. And this could be something related to critical scenarios for the policy. And StressDream steers the imaginations by updating the world model's initial noise by backpropagating gradients from the VLM all the way through the initial noise space. And it is conducted at only inference time without changing the world model itself. So that we can use this algorithm for any kind of video world models that is using a diffusion model. And this optimization can be iterated over several steps during inference time to steer the imaginations. But the key challenge here is balancing plausibility. You may have noticed that the Gaussian distribution here, shown here, looks a bit strange. Actually, a high-dimensional Gaussian distribution is strongly concentrated in a high probability mass region, known as typical set, where most training time sample noises lie. And this makes the optimization of the Gaussian noise really tricky and annoying. And a naive optimization can perturb this high-dimensional Gaussian noise into a low probability mass or out-of-distribution noise so that it no longer looks like a Gaussian sample. So this unconstrained noise, which could be lies in a low probability mass region, leads to an implausible generation look like this, trivially achieving a semantic objective while losing plausibility. So the plausibility objective of StressDream therefore keeps the high dimensional initial noise within the Gaussian distribution's typical set during the optimization, preserving the plausibility of the generated outcomes. And actually, the typical set of Gaussian distribution is different from probability density that is typically used as a regularizer. And this is because the high dimensional space also depends on the volume of that space. So take the zero vector as an example like this. And although it has the highest probability density under the Gaussian distribution, such a vector is extremely unlikely to be ever sampled in this 1 million dimensional space or just high dimensional space, because the volume around the space single point is vanishingly small. So if the noise is pushed down to such a zero vector, for example, it can become an out-of-distribution input to the world model, leading to an implausible imagination. So the plausible objective of StressDream therefore adds penalties during optimization to preserve this typicality of the noise. For example, it preserves the norm of noise and prevents local correlations or adversarial patterns over dimensions, or abnormal spectral patterns from emerging in the optimized noise like this. So in sum, StressDream combines the plausibility objective, that is keeping the optimized noise in the typical set of the noise, with the VLM-based semantic objective that generates high impact, yet plausible imaginations. So as you can see in the video, with this plausible objective and semantic objective, we finally generated a plausible imaginations that is showing failure events with the same action input to same action inputs. So StressDream, by steering imaginations, enables robust policy evaluation improvement. And I will first demonstrate its capability for robust policy evaluation in the following setup. We use the same frozen video world model. And to simulate a policy evaluation setup, we provide only the initial image and the action sequences of failure trajectories I collected. And we test whether the imaginations from this input can reveal the failure events in the imaginations. And we mainly compare the nominal imaginations from random noise and the steered imaginations. So here, the video on the left is the nominal imagination generated from just randomly sampled noise, while the imagination on the right is generated by the same world model, but using the noise steered at inference time. And here the task is to pour coffee beans into a bowl. And as you can see, StressDream imagines the coffee beans spilling with the same action, while the nominal imaginations does not imagine this task failure events. In this sense, the candy bag is open, and we ask whether the sticky candies can spill out of the bag. And this is, as the candy bears inside these bags are very sticky, such an event is very unlikely, even when the bag is intentionally shaken, but this is still plausible outcome. And as shown here, only StressDream imagines this rare but plausible outcomes like this. In another example, we place a knife high above the table into the bowl, and StressDream imagines the knife bounce out of the bowl and falling onto the table, while the nominal imaginations missed it and imagining an optimistic outcome. StressDream can also be applied to driving OR models, where imaginations are subject to high aleatoric uncertainty due to the behaviors of agents other than the ego vehicle, where the ego agents doesn't have any control over in the action input. And here, under the same ego action, StressDream imagines a collision caused by the lead vehicle braking hard, while the nominal imaginations does not capture this event. Similarly, StressDream can account for uncertainty in the behavior of a pedestrian in front of the ego vehicle. So the nominal imaginations predicts an optimistic future in which the pedestrian moves onto the sidewalk, while StressDream imagines the pedestrian remaining in the vehicle's path, which is safely critical. So for the quantitative evaluation, we use 100 failure trajectories across 6 manipulation tests, and StressDream detects these possible failures much more reliably and robustly in word model imaginations. At the same time, the steered imaginations remain plausible rather than hallucinating on implausible outcomes. For example, when the bag was closed, and the closed bag is visible from the image, so the conditional future distribution from that image does not include any spilling events. And therefore, no spill is imagined even with steering using the StressDream. And similarly, when the candy bag is simply dropped without being intentionally shaken as before, no spill is imagined because such an event is unlikely. And this example qualitatively shows that StressDream steering remains grounded in plausible outcomes rather than just hallucinating an implausible outcome to just trivially satisfy the semantic objective using VLMs. Lastly, we show that this robust policy evaluation can actually lead to a policy improvement. We test this by fine-tuning a behavior cloning policy, specifically the vision language action model, Pi 0.5. So we use the exactly same expert trajectories, all of which were successful at data collection time, but not all these trajectories are created equal. Probably some trajectories were not robust, risky, but it just succeeded at data collection time, probably because I was just lucky. So we therefore evaluate each trajectory through word model imaginations and downweight demonstrations that lead to failure in the imagined futures. So on the left is the policy fine-tuned using nominal imaginations, while on the right is the policy fine-tuned using steered imaginations. Here the task is again putting the copy back in the container. And interestingly, the robust policy fine-tuned with the steered imaginations actually tilts the bag whenever it's gripping and places it near the edge of the container to reduce the risk of spilling. Here, the robust policy moves the cup closer to the center and keeps it at a lower height, preventing the beans from spilling. In contrast, the policy fine-tuned with a nominal imaginations causes a spill. Here, the task is to pick up the bottom blue utensil from a stack, and the robust policy actually tilts while picking it up and lifting, preventing the top red utensil from falling outside the green plate. And lastly, this is the knife example again. The robust policy places the knife more gently into the bowl in a lower height, minimizing the risk of falling it out of the bowl. The quantitative results show an increase in success rate, which comes from the StressDream's ability to steer the imaginations. So not all successful demonstrations are created equal, and this steering process, promotes robust action that remains safe even under worst-case plausible outcomes, achieving robustness to aleatoric uncertainty in word models. So the main takeaway from this work is that we can learn policies that are robust to aleatoric uncertainty in the word model by steering its imaginations toward high impact but plausible outcomes. For diffusion-based video word models, this steering can be achieved by optimizing its initial noise. And this enables robust policy evaluation and improvement by explicitly accounting for the aleatoric uncertainty of the word model. Algorithmically, constraining the optimized noise to remain within the typical set of the high-dimensional Gaussian distribution was very essential for keeping the steered imagination plausible. It keeps the noise in distribution and thus the imagination from that noise. So in this talk, I presented methods for making policy learning using uncertain worry model imaginations robust. And this was done by mitigating two sources of uncertainty. First, epistemic uncertainty through out-of-distribution detection and avoidance. And also aleatoric uncertainty through steering worry model imaginations. And we can now revisit the central thesis statement. Visuomotor policy learning in worry models can be made robust by mitigating both epistemic and aleatoric uncertainties. In conclusion, this thesis showed that reliable global learning requires not only predicting the future outcomes using worry models, but also need to mitigate the uncertainty in those predictions by detecting and avoiding when they are lacking knowledges, thus they are losing its reliability, and also reasoning about plausible outcomes when the future is inherently uncertain. So before I end the talk, I want to thank all my committees of 4 professors again, Andrea, Max, Jeff, and Professor Michelle. And I want to specifically thank my advisor, Andrea, for her support and future supports for at least 3 years. I also want to thank my great lab members. I will not mention each name because they are not here, but all in common under the control of Andrea. And lastly, and most importantly, I want to really thank to my wife, who is beautiful, gorgeous, whatever else, who married to me and relocated to Pittsburgh with me and living with me. Okay, that's it. I'll be more than happy to answer 2 questions. Thank you.
Thank you, Junwon. Let's start with Max.